So, to summarize all this discussion of the constraints on complex learning systems, we've gone through a logic that links the practical considerations in red along the top to a range of architectural constraints. We've shown that these practical considerations constrain the architectural form of any sufficiently complex learning system, where sufficiently complex means that the number of behaviours which must be learned is sufficiently large relative to the available physical information processing resources. And we've ended up with some fairly specific constraints on the way in which the physical resources of a system will have to be organised and on the ways the information will have to be processed within those resources. We've defined the need for a modular hierarchy of condition definition and detection with some tight limits on changes to conditions. And those tight limits need to be implemented by a separate change manager. There has to be a separate subsystem which interprets condition detections as behavioral recommendations, where individual components in that component hierarchy correspond with behaviours. There's a need for some special mechanisms like frequency modulation to make the best use of resources. And this is a list of the detailed key constraints that we've identified. But remember, these constraints aren't absolute. They're tendencies that become stronger and stronger as the number of different behaviours to be learned increases relative to the physical information processes available to the system. However, because of the very strong natural selection pressures on brains, these properties can effectively be regarded as predictions about brain architecture. And what we're going to do in the next few sections is go through each of these properties and look at how the anatomy and physiology we covered earlier on matches the predictions. But let's start with a diagram of the architecture. The highest level prediction is a physical separation between two major subsystems, a modular hierarchy of condition detection and a component hierarchy of behaviour selection, looking like this. I've also been calling the modular hierarchy clustering and the component hierarchy competition. The modular hierarchy communicates lots of receptive field detections to the component hierarchy. The component hierarchy, or competition, interprets each receptive field detection as a recommendation in favour of a range of different behaviours, each recommendation having a different weight. The competition subsystem determines and implements the behaviour that's most strongly recommended across all the currently detected receptive fields. Most often, the implementation of the selected behaviour is a release of information into, out of, or within the modular hierarchy, so the selection is communicated back from the component hierarchy. Behaviours targeting the environment are implemented by release of information from clustering to drive, for example, muscles. Within the condition definition and detection subsystem, different areas detect conditions on different levels of complexity. And you can expect a couple of special purpose areas. One detects conditions that are effective for recommending changes to other conditions and determines where in the modular hierarchy any changes will occur. The other detects conditions that are effective for recommending different general types of behaviour that are particularly important, like aggressive, fearful, or food-seeking behaviours. More detailed subsystems are also predicted within the behaviour recommendation subsystem, including separate selection of strategic and more tactical behaviours, and so on. Then, because behaviours are most often implemented by information flows in and out of the clustering subsystem, an information flow management subsystem is needed. And sometimes the exact timing of release may be critical, so there'll be a subsystem that manages that timing. And finally, there'll be a subsystem that records sequences of behaviours that often take place in the same order, and when appropriate, will execute complete sequences rapidly and accurately. So that's the expected physical architecture. And we'll be going through the anatomy and physiology to see that it's possible to identify in the brain different anatomical structures that correspond with these theoretically predicted subsystems. The cortex corresponds with the modular hierarchy of condition definition, the hippocampal system with the change manager. The amygdala, plus also the hypothalamus, correspond with the subsystem that places priorities on different general types of behaviours. The basal ganglia with selection of strategic, tactical and detailed behaviours. The thalamus with information release management, the basal forebrain with the timing of information releases, and the cerebellum with the management of frequently used sequences of behaviours. So, in the next few sections, we're going to go through each of these structures, looking at the evidence that they are indeed performing these roles. Now, as I pointed out earlier, this separation between clustering and competition is analogous with the separation between memory and processing in an electronic system, where all the features are defined under external intellectual control. And both types of separation exist for analogous reasons. The pressure of practical considerations like resource constraints and modifiability. The major separations also mean that there are two types of information processes, although the brain and current computer architectures use completely different types. But in both cases, the physical resources are organized to support the information process types. And although the information processes in the brain are qualitatively different, another analogy with electronic systems is that they provide a way to establish the hierarchies of description needed for system understanding. Remember that the ubiquity of the instruction and data paradigms makes it possible to map from high-level, more approximate descriptions to more precise, but therefore much more detailed descriptions, and vice versa. And it's this mapping capability that makes intuitively satisfying understanding possible. And we've talked about how this works for electronic systems, breaking up high-level instructions into combinations and sequences of more detailed instructions and so on, where at each level more detailed physical resources carry out more detailed but qualitatively similar information processes. And as we're about to discuss in the case of the brain, there's analogous hierarchies that are created by natural selection. Now obviously they're not created by natural selection so that people can understand the brain. Rather, they're a side effect of the needs to minimize resources and learn without interference with prior learning and so on. And as we'll see, this means that we can use these information models to map from a high-level description of a cognitive phenomenon, like remembering an event, say, through descriptions in terms of anatomy, physiology and chemistry to create an intuitively satisfying understanding of how the physical brain performs higher cognitive functions.